entrepreneur and investor with a focus on cybersecurity. He has started up, gotten bought, and repeated this a few times. And now he is an advisor who advises people on starting up companies, getting bought, and repeating that. He is also director at CrowdStrike and an associate at MIT Media Lab. Just checking the time to make sure that we start on time, and let's start talking now on the scale of cybersecurity. Please give a warm welcome to Vincenzo.
So, hi everyone, thanks for being here. As Karen said, I have made a few changes to my career, but my background is originally technical. And what I want to do today is to talk about a trend that I think we sort of take for granted, and it's to some extent obvious, but also underappreciated, and that is cloud scale in security. Specifically, when I say cloud scale, what I mean is the ability to process fairly large amounts of data, as well as spawn computing power with ease, and how that has played a role in our industry in the past decade or so. But before I talk about that, I think some context is important. So I joined the industry about 15 years ago, and back in the days, even a place like the Congress was a much smaller place. It was to some extent cozier, and the community was tight-knit. The industry was fairly niche. And then something happened around 2010. People realized that there were more and more state-sponsored attacks being carried out, from Operation Aurora against Google to the Mandiant report, APT1, that was the first report to document how the Chinese PLA was hacking let's call it the Western world infrastructure for IP theft. And that changed a lot for the industry. There have been two significant changes because of all of this attention. The first one is notoriety. We went from being, as I said, a relatively unknown industry to something that everyone's talk about. If you open any kind of newspaper, there's almost always an article on cybersecurity. Boardrooms talk about cybersecurity. And in a sense, again, back when I joined, cybersecurity wasn't a thing. It used to be called InfoSec. And now very few people know what InfoSec even means. So notoriety is one thing, but notoriety is not the only thing that changed. The other thing that changed is the amount of money deployed in the sector. So back in 2004, depending on the estimate you trust, the total spending for cybersecurity was between $3.5 to $10 billion. Today is over $120 billion. And so it kind of looks exponential. But the spending came with almost like a very significant change in the type of players that are in the industry today. So a lot of the traditional vendors that used to sell security software have kind of disappeared. And what you have today are two kinds of player largely. You have the big tech vendors, so you have companies like Google, Amazon, Apple, and so on and so forth, that have sort of decided to take security more seriously. Some of them are trying to monetize security, others are trying to use it as a sort of like slogan to sell more phones. The other group of people or entities are large cloud-based security vendors. And what both groups have in common is that they're using more and more sort of like cloud scale and cloud resources to try to tackle security problems. And so what I want to discuss today is, from a somewhat technical perspective, how scale has made a significant impact in the way we approach problems, but also in the kind of people that we have in the industry today. So what I'm going to do is to give you a few examples of the change that we've gone through. And I think one of the important things to keep in mind is that what scale has done, at least in the past decade, is it has given defense a significant edge over offense. It's not necessarily here to stay, but I think it's an important trend that it's somewhat overlooked. So let me start with endpoint security. So back in the 80s, a few people started to toy with this idea of IDS systems. And the idea behind an IDS system is pretty straightforward. You want to create a baseline benign behavior for a machine, and then if that machine starts to exhibit anomalous behavior, you would flag that as potentially malicious. This was the first paper published on host-based IDS systems. Now, the problem with host-based IDS systems is that they never actually quite made it as a commercial product. And the reason for this, there were largely two reasons for this. The first one is that it was really hard to interpret results. So it was really hard to figure out, hey, here's an anomaly, and this is why this anomaly might actually be a security incident. The second problem was you had a lot of false positives, and it was kind of hard to establish a benign baseline on a single machine because you had a lot of variance on how the individual machine would behave. So what happened is that commercially we kind of got stuck with antivirus vendors and signatures for a very long time. Now, fast forward to 2013, as I mentioned, the APT1 report came out. AV companies actually admitted that they weren't that useful at detecting stuff like Stuxnet or Flame. And so there was kind of like a new kid on the block, and the buzzword name for it was EDR, so endpoint detection and response. But when you strip EDR from like the marketing fluff, what EDR really is effectively a host-based intrusion detection system at scale. So in other words, scale, an ability to have cloud scale has made IDS systems possible in two ways. The first one is that because you actually now have this sort of like data lake with a number of machines, you have much larger data sets to train and test detections on. What that means is it's much easier to establish the benign baseline, and it's much easier to create proper detections that don't detect just malware, but also sort of like malware-less attacks. The other thing is that EDR vendors and also companies that have internal EDR systems have, to a large extent, economy of scale. And what that means is you can actually have a team of analysts that can create explanation and sort of an ontology to explain why a given detection might actually represent a security incident. On top of it, because you have this data lake, you're now able to mine that threat data to figure out new attack patterns that you weren't aware of in the past. So this in itself is a pretty significant achievement because we finally managed to move away from signatures to something that works much better and is able to detect a broader range of attacks. But the other thing that EDR systems solved, sort of like as a side effect, is the data sharing problem. So if you've been around the industry for a long time, there have been many attempts at sharing threat data across different entities. And they all kind of failed because it was really hard to establish sort of like a protocol to share this data. But implicitly, what EDR has done is to force people to share and collect threat intelligence data and just in general data from endpoints. And so now you have the vendors being the sort of implicitly trusted third party that can use that data to write detections that can be applied to all the systems, not just an individual company or an individual machine. And the result of that, the implication of that, is that the meme that the attacker only needs to get it right once and the defender needs to get it right all the time is actually not that true anymore. Because in the past, you were in a situation where if you had an offensive infrastructure, where it was servers, where it was exploit chains, you could more often than not reuse them over and over again. Even if you had malware, all you had to do was to slightly mutate the sample and you would pass any kind of detection. But today, that is not true anymore. In most cases, if you get detected on one machine, all of a sudden, all your offensive infrastructure has to be scrapped, and you need to start from scratch. This is the first example, and I think in itself is quite significant. The second example that I want to talk about is fuzzing. And fuzzing is interesting also for another reason, which is it gives us a glimpse into what I think the future might look like. So as you're probably familiar if you've done any AppSec work in the past, fuzzing has been sort of like a staple in the AppSec arsenal for a very long time. But in the past probably 5 years or so, fuzzing has gone through some kind of renaissance in the sense that two things have changed, two things have improved massively. The first one is that we finally managed to find a better way to assess the fitness of the fitness function that we use to guide fuzzing. So a few years ago, somebody called Michael Zaleski released a fuzzer called AFL. And one of the primary intuitions behind AFL was that you could actually, instead of using code coverage to drive the fuzzer, you could use path coverage to drive the fuzzer. And that turned fuzzing in a much more effective instrument to find bugs. But the second intuition that I think is even more important and that changed fuzzing significantly is the fact that as far as fuzzing is concerned, speed is more important than smarts in a way. And what I mean by this is that when you look at AFL as an example is an extremely dumb fuzzer. It does stuff like byte flipping, bit flipping. It has very simple strategies for mutation. But what AFL does very well is an extremely optimized piece of C code, and it scales very well. And so you are in a situation where if you have a reasonably good server where you can run AFL, you can synthesize a very complex file formats in very few iterations. And what I find amazing is that this intuition doesn't apply just to file formats. This intuition applies to much more complicated state machines. So the other example that I want to talk about as far as fuzzing goes is cluster fuzz. Cluster fuzz is a fuzzing harness used by the Chrome team to find bugs in Chrome. And cluster fuzz has been around for about 6 years. In the span of 6 years, cluster fuzz found 16,000 bugs in Chrome alone, plus another 11,000 bugs in a bunch of open source projects. If you compare cluster fuzz with the second most successful fuzzer out there for JavaScript engines, you'll find that the second fuzzer called JS FunFuzz found about 6,000 bugs in the span of 8 to 9 years. And if you look at the code, the main difference between the two is not the mutation engine. The mutation engine is actually pretty similar. Cluster fuzz doesn't do anything particularly fancy. But what cluster fuzz does very well is that it scales massively. So cluster fuzz today runs on about 25,000 cores. And so with fuzzing, we are now at a stage where the bug churn is so high that defense, again, as an advantage compared to offense, because it becomes much quicker to fix bugs than it becomes to fix exploit chains, which would have been unthinkable just a few years ago. The last example that I want to bring up is a slightly different one. So a few months ago, the tag team at Google found in the wild a server that was used for a watering hole attack. And it was thought that this server was used against Chinese Muslim dissidents. But what's interesting is that the way you would detect this kind of attack in the past was that you would have a compromised device, and you would sort of like work backwards from there. You would try to figure out how the device got compromised. What's interesting is that the way they found the server was effectively to mine their local copy of the internet. And so again, this is another example of scale that gives a significant advantage to defense versus offense. So in all of these examples that I brought up, I think when you look deeper into them, you realize that it's not that the state of security has improved because we necessarily got better at security. It's that it has improved because we got better at handling large amounts of data, storing large amounts of data, and spawning computing power and resources quickly when needed. So if that is true, then one of the other thing to realize is that in many of these cases, when you look back at the examples that I brought up, it actually is the case that the problem at scale looks very different from the problem at a much smaller scale, and the solution as a result is very different. So I'm going to use a silly example to try to drive the point home. Let's say that your job is to audit this function, and so you need to find bugs in this function. In case you're not familiar with C code, the problem here is that you can overflow or underflow that buffer at your pleasure just by passing a random value for pause. Now, if you were to manually audit this thing, or if your job was to audit this function, well, you would have many tools you could use. You could do manual code auditing, you could use a symbolic execution engine, you could use a fuzzer, you could use static analysis. And a lot of the solutions that are optimal for this case end up being completely useless if now your task becomes to audit this function. And this is because the state machine that this function implements is so complex that a lot of those tools don't scale to get here. And now for a lot of the problems I've talked about, we kind of face the same situation where the solution at scale and the problem at scale looks very different. And so one realization is that engineering skills today are actually more important than security skills in many ways. So when you think back at fuzzes like cluster fuzz or AFL, or again, EDR tools, what matters there is not really any kind of security expertise. What matters there is the ability to design systems that scale arbitrarily well in sort of like their backend, to write code that is very performant. And none of this has really much to do with traditional security skills. The other thing you realize is when you combine these two things is that a lot of what we consider research is happening in a different world to some extent. So about 6 years ago, I gave a talk at a conference called CCS, and it's an academic conference. And basically my message there was that if academia wanted to do research that was relevant to the industry, they had to talk to the industry more. And I think we're now reached the point where this is true for industry in the sense that if we want to still produce significant research at places like CCC, we are kind of in a bad spot because a lot of the innovation that is practical in the real world is happening in very large environments that few of us have access to. And I'm going to talk a bit more about this in a second. But before I do, there is a question that I think is important to digress on a bit. And this is the question of, have we changed significantly as an industry? Are we in sort of like a new age of the industry? And I think that if you were to split the industry in phases, we left the kind of like artisanal phase, the phase where what mattered the most was security knowledge. And we're now in a phase where we have this large-scale expert systems that require significantly more engineering skills than they require security skills, but they still take input from kind of like security practitioners. And I think there is a question of, is this it? Or is this the kind of like where the industry is going to stay, or is there more to come? I know better than to make predictions in security, because most of the times they tend to be wrong. But I want to draw a parallel. And that parallel is with another industry, and it's machine learning. So somebody called Rich Sutton, who's one of the godfathers of machine learning, wrote an essay called The Bitter Truth. And in that essay, he reflects on many decades of machine learning work. And what he says in the essay is that people tried for a very long time to embed knowledge in machine learning systems. The rationale was that if you could embed knowledge, you could build smarter systems. But it turns out that what actually worked were things that scale arbitrarily well with more computational power and more storage capabilities. And so what he realized was that what actually worked for machine learning was search and learning. And when you look at stuff like AlphaGo, today, AlphaGo works not really because it has a lot of Go knowledge. It works because it has a lot of computing power. It has the ability to train itself faster and faster. And so there is a question of how much of this can potentially port to security. Obviously, security is a bit different. It's more adversarial in nature, so it's not quite the same thing. But I think we have only scratched the surface of what can be done as far as reaching a newer level of automation where security knowledge will matter less and less. So I want to go back to the AFL example that I brought up earlier. Because one way to think about AFL is to think about it as a reinforcement learning fuzzer. And what I mean by this is, in this slide, what AFL was capable to do was to take one single JPEG file, and in the span of about 1,200 iteration that were completely random dumb mutation, go to another well-formed JPEG file. And when you think about it, this is an amazing achievement because there is no knowledge of the file format in AFL. And so we are now more and more building systems that do not require any kind of expert knowledge as far as security is concerned. The other example that I want to talk about is the Cyber Grand Challenge. So DARPA a few years ago started this competition called Cyber Grand Challenge. And the idea behind Cyber Grand Challenge was to try to answer the question of, can you automatically do exploit generation? Can you automatically do patch generation? And obviously, they did it on somewhat toy environments. But if you talk today to anybody who does automatic exploit generation research, they'll tell you that we're probably 5 years away from being able to automatically synthesize non-trivial exploits, which is an amazing achievement, because if you asked anybody 5 years ago, most people, myself included, would tell you that that time would not come anytime soon. The third example that I want to bring up is something called Amazon Macy, which is a new service released by Amazon. And what it does is basically uses machine learning to try to automatically identify PII information and intellectual property in the data you store with AWS, and then try to give you a better sense of what happens to that data. So in all of these cases, when you think about them, again, it's a scenario where there is very little security expertise needed. What matters more is engineering skills. So everything I've said so far is reasonably positive for scale. It's a positive scale is a positive sort of like case for scale. But I think that there is another side of scale that is worth touching on, and I think especially to this audience is important to think about. And the other side of scale is that scale breeds centralization. And so to the point I was making earlier about where is research happening, where is real-world applicable research happening, and that happens increasingly in places like Amazon or Google or large security vendors or some intelligence agencies. And so what that means is the barriers to entry to the field are significantly higher. So I said earlier that I joined the industry about 15 years ago. Back then I was still in high school, and one of the things that was cool about the industry for me was that as long as you had a reasonably decent internet connection and a laptop, you could contribute to the top of the industry. You could see what everyone was up to. You could do research that was relevant to what the industry was working on. But today, the same sort of like 15, 16-year-old kid in high school would have a much harder time contributing to the industry. And so we are in a situation where, because scale breeds centralization, we are in a situation where we will likely increase the barrier of entry to a point where if you want to contribute meaningfully to security, you will have to go through a very standardized path where you probably do computer science and then you go work for a big tech company. And that's not necessarily a positive. So I think the same Kranzberg principle applies to scale in a sense, where it has done a lot of positive things for the sector, but it also comes with some consequences. And if there is one takeaway from this talk that I would like you to have, is to think about how much something that is pretty mundane that we take for granted in our day-to-day has changed the industry, and how much that will probably contribute to the next phase of the industry. And not just from a technical standpoint, it's not just that the solutions we use today are much different from what we used to use, but also from the kind of people that are part of the industry and the community. And that's all I had. Thank you for listening.
Thank you very much. We have time for questions. So if you have any questions for Vincenzo, please line up behind the microphones that are marked with numbers, and I will give you a signal if you can ask a question. We also have our wonderful signal angels that have been keeping an eye on the internet to see if there are any questions from either Twitter, Mastodon, or IRC. Are there any questions from the internet? We'll just have the mic for microphone number 9 to be turned on, and then we'll have a question from the internet for Vincenzo. And please don't be shy. Line up behind the microphones to ask any questions.
Now it's on, but actually there are no questions from the internet right now.
There must be people in the room that have some questions. I cannot see anybody lining up. Vincenzo, do you have any advice for people that want to work on cybersecurity, on scale?
I mean, as I said, I think a lot of the interesting research is happening more and more in like tech companies and similar. And so as much as it pains me, it's probably the advice is to think either whether you can find other ways to get access to large amounts of data and computational power, or maybe consider a stint in one of those places.
And we now actually have questions at microphone number 1.
Hello? Can you hear me?
Yes.
Thank you for the great talk. You're making a very strong case that information at scale has benefited security, but is there also statistical evidence for that?
So I think, well, it's a bit hard to answer the question because a lot of the people that have an incentive to answer that question are also kind of biased. But I think when you look at metrics like dwell time in terms of how much time people spend on attacker's machine, that has decreased significantly. Like it has statistically decreased significantly. As far as the other examples I brought up, like fuzzing and similar, I don't think, as far as I'm aware, there hasn't been any sort of like rigorous study around whether now we've reached the place where defense has kind of like an edge against offense. But I think if I talk to anybody who has kind of like some offensive security knowledge, or they work in offense, the overall feedback that I hear is that it's becoming much harder to keep bug chains alive for a very long time. And this is in large part not really for countermeasures. It's in large part because bugs keep churning. So there isn't a lot of statistical evidence, but from what I can gather, it seems to be the case.
We have one more question from microphone number 1.
So thank you for the interesting talk. My question goes in the direction of decentralization that you mentioned, that the large, like the hyperscalers, are converging to be the hotspots for security research. So is there any guidance you can give for us as a community how to retain access to the field and contribute?
Yeah, so I think it's an interesting situation because more and more there are open source tools that allow you to gather the data. But the problem with these data gathering exercises is not too much how to gather the data. The problem is what to gather and how to keep it. Because when you look at the cloud bill for most players, it's extraordinarily high. And unfortunately, I don't have an easy solution to that. I mean, you can use pretty cheap cloud providers, but it's still the expenditure is still an order of magnitude higher than it used to be. And I don't know, maybe academia can step up. I'm not sure.
We have one question from the internet, and you can stay at the microphone if you have another question for Vincenzo.
Yes, the internet asked that you ask a lot about fuzzing at scale, but besides OSS fuzz, are you aware of any other scaled large fuzzing infrastructure?
That is publicly available, no. But when you look, when you look, for instance, at the participants for Cyber Grand Challenge, a lot of them were effectively using significant amount of CPU power for fuzzing. So I'm not aware of any kind of like plug and play fuzzing infrastructure that you can use aside from OSS fuzz, but there is a lot, like as far as I'm aware, everyone there that does fuzzing for a living has now access to significant resources and tries to scale fuzzing infrastructure.
If we don't have any more questions, this is your last chance to run to a microphone or write a question on the internet. Then I think we should give a big round of applause to Vincenzo.
Thank you.